In this segment, we will be discussing combining different light waves. We'll start by discussing combining light waves of the same color. Of course, before doing that, we have to precise what do we mean by color. Now, if you recall this particular slide, when we discussed the electromagnetic spectrum, we have remarked, I hope you recall, that the electromagnetic spectrum includes waves from a wavelength of about 10 to the 4 centimeters to 10 to the minus 12 centimeters. We said all of these waves are electromagnetic waves. The only thing that differentiates them is their wavelengths. And visible light, what we call usually light, is electromagnetic waves that have a wavelength range of about 10 to the minus 5 centimeter. 10 to the minus 5 centimeter is about 100 nanometers, if you recall that a nanometer is 10 to the minus 9. Now, actually, visible light spans a small range of the spectrum where the wavelengths go from about 700 nanometers for red to about 400 nanometers for blue. And we have all the other colors in between. What determines the color is the wavelength. Like what determines if it is radio wave or microwaves is the wavelength. So the difference between these waves is the wavelength. Now, alternatively, we could have expressed all of these in terms of frequency, in terms of wavelength. Just remember that the frequency is just c over lambda. Now, if I had this diagram in terms of frequency, now instead of having the numbers decrease, I'm going to have increase in numbers instead. That's the only difference. But since c is constant and it's the same for all of them, I could have represented everything in terms of f. Now, going back to discussing adding waves of the same color, let's see here. We have two waves that are identical. Identical waves, they are in phase and of the same color. In phase meaning a crest corresponds to a crest and a trough corresponds to a crest. Now, when we add these two waves, the displacement of the waves are going to add up at the particular point where they meet. For example, here, if I have an amplitude 1 and an amplitude 1, the wave here is going to have an amplitude of 2. Here I have a 0 and a 0, so the amplitude of the wave at that point is going to be a 0. Here I have a minus 1 and a minus 1, so I'm going to have a minus 2 here. So what I'm going to get is a wave with twice the amplitude, which is the sum of the two waves here. This, whenever two waves are in phase, we are going to say they are going to add up constructively. We are going to say we have constructive interference. Now, the term constructive interference, the word interference or superposition of the waves, they are synonyms of the same phenomenon. So what we see is going to be something like this. Now, if the two waves are out of phase, something like this, meaning a crest is going to correspond to a trough and vice versa. In that particular case, a plus 1 amplitude is going to add up to a minus 1. That's going to result in a 0. Minus 1 plus 1 result in a 0. 0, 0, 0. So if we can check every point there, that means the waves are going to cancel out. And we have then what we call destructive interference. Now, of course, if this wave was bigger than this wave, we are still going to have, if the amplitude here is bigger than the amplitude here, we're still going to have destructive interference, but we are not going to have a zero amplitude here throughout. Now, what if the waves are slightly out of phase, not totally out of phase like here? So it's going to be somewhere between destructive interference and constructive interference, partial destructive interference. But usually we talk of the extreme cases, and everything else is going to be what's in between. Now, what happens when we mix light of different colors? You know it from art, for example. The situation becomes more intricate. It's not interference anymore. That's when you have red and blue, for example, that gives you. Okay, I'll let you tell me what does it give you, what color does it give you, and so on. Now, physically here, I have two waves, two different colors, different frequency, so different wavelengths. So here it's a larger wavelength than this one, meaning that I have a smaller frequency here than here. Larger wavelength, smaller frequency. Remember, lambda is V over F. Okay, so what do we have here? What are we going to have? Constructive interference, destructive interference, something in between? This is what we are going to get. You have learned probably with sound, when you had two wavelengths or two frequencies that are close to each other, you get beat. But in either case, what we are getting is not what we call interference. It's something else, and that's not going to be the goal of what we are talking about here. So it's not interference. The requirements for interference are that we need two or more waves. They need to have the same frequency. Alternatively, we can say the same wavelength or the same color. And they must be coherent, meaning they must have a definite phase relation. Like they can need to be in phase or out of phase, so we can compare them. If the phases are not going to be easily related, we are not going to be able to have interference. We'll get back to this in another segment.